Hey pre-calc students, in this video we're going to talk tangent and the reciprocal graphs. It's really important when we're talking tangent and the reciprocals that we understand what these functions are made of. So for instance, if I'm talking about the tangent of x, we know that tangent of x can be written as the sine of x over the cosine of x. Same is true for some of our other reciprocal trigs. I can find my cotangent of x by doing my cosine of x over sine of x, my secant of x by doing 1 over cosine of x, and we can find the cosecant of x by doing 1 over sine of x. The reason why these are important is we've already talked about sine and cosine graphs, but what we're going to be talking about in this video is how do we look at these trig, reciprocals, and tangent, and all they are what are called rational functions, meaning they're fractions, trig graphs. Before we talk rational trig graphs, we're going to quickly review rational functions that aren't trig. In a rational function, the x-intercepts are the zeros of the numerator, and the vertical asymptotes are the zero of the denominator. Here in this function, I have f of x is equal to x minus 4 divided by x plus 5. Take a minute and see if you can find the x-intercepts and the vertical asymptotes of this function. Okay, this function is going to have an x-intercept at positive 4 and a vertical asymptote at negative 5. I can confirm this by looking at the graph, where I in fact have a vertical asymptote at negative 5. As I approach negative 5, I go to infinity and negative infinity on my graph. That's creating my vertical asymptote here at negative 5, and I have an x-intercept here at positive 4. So let's take a look at how this works for trig functions. Okay, so the first thing that we're going to do is discuss our parent tangent function. The first thing that's important to note is that tangent is a rational function that is sine of x divided by cosine of x, and that is equivalent to tangent. So to find our x-intercepts, we're going to look at the zeros of the numerator. We want to know, when does sine of x equal 0? We got to think back to our unit circle. Okay, looking back at our unit circle, we know that sine is the y value, and we're trying to find the angle that makes it 0. We're going to do this in radians. So when y is 0, that's at 0, pi, 2 pi, and I could keep going 3 pi, 4 pi, 5 pi, and so on. So a good way to write this, I'm going to list out a few of them. And then what I'll actually just say is every n pi. N pi, where n is a whole number, so 1, 2, 3, 4, 5, 7 pi, 8 pi, 9 pi, so on. So every n pi. Okay, now let's talk vertical asymptotes. Our vertical asymptotes are going to come from our denominator equaling 0. These are going to happen on my unit circle when the cosine value is 0, and that's going to be every half pi. So up here at pi over 2, my cosine value is 0, 3 pi over 2, my cosine value is 0, and so on. So this is pi over 2, 3 pi over 2. Really what we're doing is we're starting with pi over 2, and we're adding a pi on. So we would add in pi on, because you're just always adding a half circle, starting at pi over 2, adding a half circle, adding a half circle to keep finding those places where the cosine value is 0. So at pi over 2, 3 pi over 2, and then every pi plus that. Okay, so let's take a look at our graph of what this looks like. The first thing I'm going to do is I'm going to place my x-intercepts. My x-intercepts of tangent are at 0, pi, 2 pi, and 3 pi, essentially starting at 0 and adding every pi. My vertical asymptotes are happening at the half pi. So I'm going to draw a vertical dotted line that I'm going to approach but not get to. Okay, so what this graph is going to look like is it's going to cross the x-axis, and then it is going to approach the vertical asymptote and go to infinity in the y values as you approach that vertical asymptote. Then it's going to, again, pick up from that vertical asymptote. It's going to cross the x-axis and it is going to approach yet another vertical asymptote. And this will kind of do this over and over and over again. Just like other trig functions, this graph repeats over and over and over, where it approaches a vertical asymptote and crosses the x-axis. So this, again, has a period because it does repeat itself. And where it starts to repeat itself is it starts at the x-axis and approaches a vertical asymptote. Then on the other side of the vertical asymptote, it goes up to the x-axis and it stops. So tangent has a period of pi. Every pi it repeats itself. So the period of tangent is pi. Okay, the last thing that we're going to talk about is our basic shape. This is going to help us with our transformations. Our basic shape of tangent starts on a midline. We still call that a midline. It's the middle of the tangent graph. It's going to start on the midline, then it has a vertical asymptote, and then it goes back to the midline after it does that vertical asymptote. So you've got a vertical asymptote in the middle of two midline values, and then that repeats over and over and over again. So our basic shape is midline, vertical asymptote, midline, and this just keeps going. Vertical asymptote, and so on. Vertical asymptote, or midline, vertical asymptote, midline, vertical asymptote, back and forth, back and forth. Next, we're going to look at the parent function of cotangent. This works almost very similar to the parent function of tangent because it is a rational function, but here the cosine is my numerator, so that's going to give me my x-intercept. The sine is my denominator, so that's going to give me my vertical asymptotes. See if you can pause the video and identify your x-intercepts and vertical asymptotes of the cotangent function. Okay, pause the video to check your work. My x-intercepts of cosine are at every half pi, so pi over 2, 3 pi over 2, 5 pi over 2, and so on. This is when cosine is 0, the numerator of cotangent. And the vertical asymptotes come from the denominator, which is sine, and this is going to happen when sine is 0. These are all the zeros, pi, 2 pi, and 3 pi. And again, these do repeat, they go on forever. Okay, so how these is going to work, cotangent, the difference between really tangent and cotangent, other than the placements of their x-intercepts and vertical asymptotes, is cotangent is a decreasing function, whereas tangent is an increasing function. Might be worth adding that to your last slide. But the way that cotangent works is I'm starting with a vertical asymptote and I'm going to decrease to my x-intercept and then approach my next vertical asymptote. I'm going to do that between every set of vertical asymptotes. I have a decreasing section, and it just repeats over and over and over again. Similar to tangent, my cotangent has a period of pi. Every pi units, this graph repeats itself. And the basic shape here starts with a vertical asymptote, then hits the midline, and then goes to another vertical asymptote. And again, alternating back and forth between these vertical asymptotes and midlines. The next two graphs that we're going to look at are the secant and cosecant graph. So starting with our secant, this is 1 over cosine. We're going to talk about the extreme values, the vertical asymptotes, the period, and the basic shape of this graph as well. First, I'm going to talk my vertical asymptotes. Vertical asymptotes, we do have a denominator here of cosine of x, so that's going to yield my vertical asymptotes. Pause the video and see if you can identify what the vertical asymptotes of secant will be. Pause the video to check your work. The values that make cosine 0, again, are all the pi over 2 and then plus a pi, so 3 pi over 2, 5 pi over 2, 7 pi over 2, and so on. Again, that would be pi over 2 plus a half circle. I also went ahead and graphed these on my parent graph. Okay, to understand the extreme values, I actually want to show you a Desmos graph of secant and cosine side by side. I think it's going to help understand what's happening to these extreme values when I do a reciprocal on cosine, getting a secant function. Okay, here I have the graph of the cosine function, which is secant's reciprocal. And what I'm going to show you is that cosine, we start cosine at a max value, and then it dips to the midline, and then it goes to the minimum, midline, and then a maximum. And this is our basic shape of cosine, and that just repeats over and over and over again. When I look at the reciprocal, something incredibly interesting happens. Every time that cosine has a max, that actually becomes a minimum value on the secant function. So max values become minimum values. And again, minimum values become maximum values. This still happens at the max value of 1 and -1. Again, mathematically speaking, we're talking about secant is 1 over the cosine value. So 1 divided by 1 is, in fact, 1, which is why we're still keeping that same value there. It's just getting turned upside down or reciprocated. So these max values become minimums. The min values become maximums. So that's a really interesting phenomenon. Let's write that down about the extremas, and then we'll start graphing. So now, instead of having a maximum of 1, we actually have a minimum of +1 and a maximum of -1. So these are our min and max values. They do happen directly between every vertical asymptote. So first I'll have a minimum value of 1, and then a maximum value of -1, a minimum value of +1, and this would just kind of keep going. I can draw my secant function, which kind of looks like u's, but they do have vertical asymptotes, so they the two u's never actually cross into each other's domain. In order to create an entire period of secant, we start at 0, which is the minimum value, and we need to complete the full cycle. So minimum to the maximum, back down to that minimum. The secant function has a period of 2 pi. And the basic shape is going to go the minimum value, a vertical asymptote, a max value, a vertical asymptote, and then back to a min value. Super confusing here, mins and maxes, because of the minimums, the maxes that became minimums, there is a gap space in the range of these functions. And so when I say I'm starting at a minimum value, I'm starting above a max value, which again, these are relative minimums and relative maximums. So this is a relative minimum, a relative maximum, a relative minimum, and there is a gap space between in our range where there are no output values of secant there. For time's sake, the graph of cosecant works just like the graph of secant, except for now we're dealing with 1 over sine. I'm going to go ahead and fill in the majority of this and then let you pause the video to make sure you copy it down, have it in your notes, but I'm not going to talk through a ton of it. Pause the video to make sure you have all the key elements of cosecant. The last thing that we'll cover in this video is how do we find transformations, or how do we apply transformations to these trig functions. So here we have an amplitude, which is not often called an amplitude in these other trig functions. We more often call them a vertical stretch or compress, which does affect the y values of the parent function. K, which is our midline, vertical shifting the y values up and down. F, which is our frequency, is a horizontal stretch or compress on the x values. And then H is our phase shift, horizontal shift on the x values of the parent function. Remember that horizontal transformations are opposite, so the frequency and the phase shifts are backwards to what you would think transformations are. And then the last thing is to calculate the period. It depends on the original function because these two different types of functions have different periods. If you're calculating the period of tangent or cotangent, you find the period by doing pi over the frequency. And for the period of secant and cosecant, you do 2 pi over the frequency to calculate their periods. Okay, we're going to identify a sketch of the graph, and then we're going to identify the key features. Okay, so the first thing that I'm going to do is identify my basic shape. I see this y equals 3 secant of pi over 4 x minus 2 plus 1. My basic shape is going to be that of a secant function. Secant functions start at a min value, have a vertical asymptote, a max value, a vertical asymptote, and a min value. To calculate my period, I need to understand whether it's what type of function it is. This is a secant, so to find my period, I'm going to do 2 pi divided by the frequency, which in this case is pi over 4. I'm going to multiply by my reciprocal, and I have a period of 8. To find my phase shift, I'm looking at the same place I would find my phase shift for my other trig functions. This is moved 2 units to the right. My vertical shift has been moved up 1 unit. This is also, think of it like a midline of y equals 1. And then I have a vertical stretch of 3. So 3 units up and down for my midline are my max and min values. And I'm actually going to do a sketch of this graph before I find my vertical asymptotes. So let me get a little bit of space here, and we're going to sketch the graph of this function. I'm going to start by sketching an x and a y axis. To start the sketch of this graph, I need to start 2 units to the right and go a total of 8 units. So I'm going to start 2 units to the right. That's my starting value. And I have to go a total of 8 units. So I'm going to go 8 units further to 10. My important y values is I do have a midline of 1. And then my amplitude, which is going to create my mins and my maxes, I'm going up 3 units and down 3 units. Okay, completing my basic shape, I'm going to start at a minimum. Now it's really important to understand that this graph is when I say a minimum, I'm not actually starting at the bottom value. Remember, secant has turned those max values into minimums. So when I say I'm starting at a minimum, I'm actually starting at the value 4, and it's going to U up from there. At the end of my graph, I'm going to be back where I started at that same max, or it's a min value, but it's a minimum of 4, which is the top value. And then right in the middle, I'm going to be on my max value, which is down here at the bottom at -2. Let's see, that value between 2 and 10, the average there is going to be 6, so that's going to be 6 and -2. Then between my max and min values, I have my vertical asymptotes. So between 2 and 6, I'll have a vertical asymptote at 4. And I'll also have a vertical asymptote between the 6 and the 10 value at 8. Now that I have my vertical asymptotes and my max and min values, I'm going to go ahead and sketch my basic graph where I am going up from my max minimum values and down from my max values. And that is my basic shape of my secant function. I did want to find my vertical asymptotes. That's why I kind of started with the graphing portion. My vertical asymptotes are falling here and here at x equals 4 and at x equals 8. And we also know that these are repeated values, so I can kind of see the pattern here is going to be every 4 units. I could keep this going at 4, 8. I would have another one at 12. I would have another one at 16. And so on for my vertical asymptotes. Okay, same question as before. We're doing this with we're going to sketch a graph, find basic features, and so on. I have y equals tangent of 1/2 x minus 4. First thing I'm going to do is identify my basic shape of tangent. Tangent starts on a middle value, then has a vertical asymptote, and goes to a middle value, and then just repeats that pattern over and over and over again, vertical asymptote, middle value, so on. To do a full period, let me back up because I do want to make sure I'm only talking about one period so I know when the period starts and ends. The period of tangent includes a middle value, a vertical asymptote, and then a middle value. All right, my period of tangent I can find by using p equals pi divided by the frequency, in this case 1/2. I can multiply by the reciprocal to simplify this. So I have a period of 2 pi. My phase shift is none. I don't have anything added to the outside or to the inside of my graph. I do have a vertical shift down 4 units. This would give me a midline of y equals -4. And I have no vertical stretch, which means this is a normal tangent function, or my vertical stretch is 1. Again, I'll find vertical asymptotes at the end. Okay, let's start graphing this. I am going to start with my x and my y axis. I do notice that I'm going to be going down 4 units. So I'm going to move my x axis up so that I can see that down 4 units pretty clearly. To start my x axis, I know that I have no phase shift, so I'm going to start at 0, and then I have a period of 2 pi, so I'll go ahead and put pi and 2 pi on there. And then I also want to set up my y values, my important y values. I have a midline of -4. And there is no vertical stretch on this graph, so it will look like a normal tangent function, not stretched. All right, so let's take a look at my basic shape. My tangent function is going to start on the midline. In this case, -4. It is going to end on the midline. And in the middle, we're going to have a vertical asymptote. So right here at pi, I'll have a vertical asymptote. Tangent we know is increasing. I think that's an important thing to say here. And so now I can draw my tangent graph where I start on what was an x-intercept, but now it's just a midline value, and I'm going to go up and down. That doesn't do a full picture of tangent, so I like to kind of continue that shape and show that full tangent graph that this repeats over and over and over again. It's important to know where our vertical asymptotes are. We have one here at pi, and then 2 pi is a midpoint, so the next one would be 3 pi, and so on. We can say this is every odd pi. Okay, the very last thing that we'll do in this video is find vertical asymptotes. If they only want you to find vertical asymptotes, sometimes it's too much to do all the things in graph. So there's a quick and easy way to find vertical asymptotes of these functions. When instructed to only find the vertical asymptotes, you can set the expression on the inside of the trig equal to the parent function's vertical asymptotes and solve. Let me explain what that means. So here I have the equation tangent pi over 3 times x plus 4, all of that minus 2. So first I'm going to use only the expression inside of the trig. So I'm going to take my expression inside of the trig. These are my horizontal changes. So these are the changes that are going to affect my vertical asymptotes, because my vertical asymptotes are x values, and so these horizontal changes affect that. So I'm going to take my expression on the inside of the equation, and I'm going to set this equal to tangent's original vertical asymptotes. Okay, so the first vertical asymptote that tangent had was pi over 2. And I can solve this equation. The first thing I'm going to start by solving this equation is I'm going to multiply by the reciprocal of this fraction outside to get rid of it. So that gives me x plus 4 is equal to 3/2, and then I can subtract 4 from both sides, which gives me a vertical asymptote at x equals -5/2. And I could keep doing this. I could do this for my other vertical asymptotes of tangent. I'll do another one. We knew that there was a vertical asymptote at 3 pi over 2, so I'm going to start with my inside equation. And again, I'm going to solve this just like the last one. Pause the video and see if you can find this vertical asymptote. And I can also do this for my equation to find all vertical asymptotes. We know that the all vertical asymptotes of tangent was that pi over 2 plus pi in, or in pi. And we can solve this equation like we did before, where we'll leave n as a variable So that way we can, again, find all of these values of my vertical asymptotes. So multiplying by the reciprocal would give me x plus 4 on one side. On the other side, I would have to distribute that reciprocal 3 over pi. So that'd be 3/2 plus 3n when I simplify. And then I could subtract 4. When I subtract 4 from both sides, I'm going to subtract it with its like term. So 3/2 minus 4 is negative 5/2. And then again, that plus 3n is just saying, okay, well, it's going to start at negative 5/2, which we saw in our first one. Our first vertical asymptote was at negative 5/2. And then to find the following ones, I can just keep adding 3n onto it. So negative 5/2 plus 3 is positive 1/2. And I could keep that going to find all following ones, adding 3 each time. If I did, my next one would be then 3.5, and then 6.5, and then 9.5, and so on.